Hi, Ashish. Let's start the session at 9:05. Let's wait if any other participants also join. All right. So, a very good evening to all of you. Today, we are going to be covering another important topic called as breadth first search and depth first search. We have already covered this under our DSA topics, and it was one of the important topics. And we had covered it, I think, during the last few classes of DSA. So let's first quickly just recapitulate what is depth first search and breadth first search. So when it comes to DFS and BFS, they are two important traversal techniques. Okay, so we have a graph and the traversal technique that is used in the graph. These are those two types of traversal techniques that we largely use when it comes to graphs, and they are types of algorithms also. So let us understand what exactly it is. So when we are talking about DFS, that is depth first search. So what happens in depth first search is, assume that we have a graph of this kind. We have A, which is leading to B, then C, and this in turn is leading to D and E. And then we are having F here. All right. Now look at the connections. I am creating connections here. Okay. So when I'm talking about depth first search, how does the traversal happen? Obviously, we start at node A. After we start at node A, we head to node B. Now we are talking about depth. Depth means it is going to go as deep as possible in your graph. And once that depth is exhausted, it goes back to your root node and from there tries to move about or branch about. Okay. So here, what is the depth? We started with root node A, then we moved to node B, then B is going deeper until node D. So what is it? The way it's traversed is, we have A, which leads to B, then it leads to D. All right. Now from D, it is going to go back to B and it is then going to traverse node E. From D, it is going to head to node E. All right, then let's write node E. After this, now there is nothing to go deeper. So what it's going to do, it's going back to the node. Now, which is the node? It's going back to the root node A. So once it goes back to root node A is going to move to node C then. Okay, it's going to traverse node C. So E, then next node that we are going to read is C. Then again, as deeper as it can go, node C will lead you to node F. So F. So this is your depth first search. A, B, D, E, C, F. All right. This is the order in which your graph is going to be traversed when we are talking about D, F, S, depth first search. All right. When we are talking about this, this is going to be a traversal. Now, when we are talking about BFS, breadth first search, then what happens? When we are talking about breadth first search, then look at the traversal. In breadth first search, we are going to be covering each level of the node and then head to the next level. We'll be covering each level of the node and then head to the next level. So here, when we have these, what are we going to do is, first, you start with node A, obviously. So let us mention node A. After node A, where is it going to head to? It is going to move towards your node B. All right, node B is also done. Now, breadth first search. Look at it horizontally. What is the next node at the same level as node B? You have node C. All right, so let us finish node C. What did it do? It completed the same level nodes. Horizontally, it completed the same level nodes. Now it is going to move to the next node. Now, what is the next node we have? It is going to be, it is going to come back to B, and then from here it's going to the third level of the tree. That is this now. So here, what do we read? We are going to read the next node, that is D. Then it's going to read the next node, that is E. We are completing the same level nodes. And then finally, it's going to read the last level, last node in that level, that is F. So what happened? We are completing it level wise. This becomes one level, then this becomes the next level. So this is the way breadth first search is completed. Okay, you can see the order, the difference in our traversal technique when it comes to DFS, how it's done, when it comes to BFS, how it's done. In DFS, we use a stack. Usually we use a stack. So y'all might be able to recollect that we had used a stack when we were dealing with DFS, or we use a recursion. What is recursion? Recursion is a type of a function. It's a recursive function that we use, wherein that function keeps calling itself again and again until the end case is until the end case becomes true. The base case needs to become true. Until then, the function keeps calling itself repeatedly. All right. So in DFS, we either use a stack or a recursion. And in BFS, we use queues. What do we use? We use your queues, Queuue. Okay, this is the main difference between DFS and BFS. This is the traversal techniques. I already showed you the traversal techniques, and in BFS, I showed you how exactly the graph will be traversed and how do we store it? We store it in the form of a queue. Now, what are the use cases of your DFS and BFS? DFS is usually utilized whenever you want to solve any maze, you want to do some pathfinding. In such cases, DFS is utilized. And then how is BFS utilized? BFS is usually utilized to make a copy of something accurately and not make multiple recursive calls for it. And then you want to find out some shortest path in a graph where weights are not added to the graph. You want to figure out the shortest path. In such cases, BFS is utilized. But largely, when it comes to your problem solving technique, we utilize your DFS at the max. Okay, compared to your BFS, DFS is used more commonly and more often. As in, you'll find such use cases that you end up using DFS. So that's about our session today, what exactly we'll be covering in the session. This is the gist of it. So let us dive deeper and understand that what are the various problems that are here and how exactly can we solve them. Okay. So the very first problem that we have here is cloning the graph. All right, so all of these questions are going to be graph questions, or they are going to be in the form of matrices. Okay, because graphs, you cannot represent it in any other form. So we are going to have matrices whenever it comes to graphs. Okay. So we need to clone a graph here. So we are given a graph, we need to make an exact copy of it. So in what use cases or in what scenarios is this going to be useful? You might be wondering that, right? Why exactly do you want to clone a graph? So many a times what happens when we are designing a game or making a game, anything as such, right? At some point of time, we want to take a copy of our current scenario. Okay, and we want to keep that as load game option, right? You all might have seen whenever you're playing a lot of games, there's some point where you pause the game. So, or you give it as save or checkpoint, right? So after certain number of days, you want to continue from there. So what happens? We would have created an exact copy of your game, and that's lying in the memory. And whenever you click on load, it loads from the memory that copy of the game which you had saved. So in such cases, these kind of scenarios will play useful. That's the reason we are learning how to clone a graph. Okay, the use case is something of this kind. I'm just giving you one rough example where exactly cloning can be utilized, cloning of the graphs, but there are many such examples where this kind of cloning is required so that there's no change and it happens efficiently. There is no redundancy. There are no multiple copies of your nodes. In fact, there ends up only a single copy of the node. Let's understand the intuition behind this. What happens here? So now we need to make an exact copy of the graph. It should not have any change. Now each node should have the same value, whatever is there in the original graph, and each node has to be connected in the same way like it is connected in the original graph. Okay. Now the only thing that can be different is this is stored in one memory location. This copy is going to be stored in another memory location. This is the only difference. Else they need to be exact carbon copies of each other. All right. Now the key challenge is the way that we can handle their connections. What happens in a graph? A graph can be either cyclic or acyclic. What do you mean by cyclic graph? Cyclic graph means each and every node is interconnected to each other. Somewhere it ends up as a cycle. Now, whenever you encounter such type of graphs, it is difficult to maintain that connection with the graphs. What happens? One node is connected to the next node, and this node can be connected to some other node. So when you are trying to make connections, you can duplicate those nodes many times, right? But we don't want that duplication to happen. We are utilizing BFS or breadth first search here so that it can keep track of all the nodes or all the neighbors that you have visited. Once you visit that node, memoization, recollect the topic of memoization which we completed in during our problem solving. What happens in memoization? It keeps track of our things that we have created or visited, right? So here exactly it's going to keep track of the nodes that we have visited whenever we try to make another cyclic connection. Okay, we don't end up creating that node again. Instead, we check our dictionary. If that node already exists, we are just going to pull that and create a pull that and put it up as a connection there. We are not going to create another copy. We are just going to take that from the dictionary and put it there because it's already been visited. Okay, we avoid any kind of infinite loops. Because of this, infinite loops are avoided. The next thing, we utilize a dictionary or a hash map, right? During our problem solving, I did tell you that dictionary is put up in the form of a hash map wherein the memory location as well as what is being created is stored, right? After that, now the breadth first search helps us to systematically explore all the nodes and connections. We can do it one by one at a time, and in a order, right? So that's what BFS enables us to do. That's the reason we are going to be utilizing. The same thing can be done utilizing your DFS or your depth first search. But here, just to give you an idea how exactly BFS is utilized, I'm going to use BFS in this particular problem. You can do the same solution utilizing DFS. That's absolutely fine. You'll get a accurate clone of the graph, but we are going to be utilizing BFS so that you also get the hang of how to deploy BFS. All right. Now, I hope that intuition is clear to you. Here, simple thing, we are going to maintain a hash map or a dictionary, which is going to keep track of all the nodes you have visited so that redundant copies don't end up being created. The next is we are going to be utilizing queues here because we are utilizing BFS. It has queues in it. And after utilizing queues, simple, once we put up all the elements that we are visiting, we just keep popping out so that we can establish the connections between the node. Okay, so it's going to be a simple loop, simple function, which is going to consist of your queue functions. All right, now assume that we have a node of this kind: 1, 2, 3, and 4. This is a graph that we have. Okay. Now 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, and 4 is connected to 1. Now, if you try creating these nodes, every time if you try creating this node, 1 is connected to 2. You created node 1, then you move to node 2, and you try to establish a connection between 1 and 2. Done. Very good. Now from node 2, you move to node 3. Okay, node 3 created, you try to establish a connection between 2 and 3. But when you are trying to establish a connection between 2 and 3, you don't end up creating 2 again. Instead, what is maintained? The visited node is maintained, right? So in that visited node, we have already visited 2, so it is lying in your visited node. We pull out 2 from there and make a connection with 3 for it. Okay, then from 3 we move to 4. We create a new node 4, but now we don't create a new node for 3. Instead, we check your visited node. In that 3 is lying there. We pull out 3 and make a connection with 4. Okay, now 4 has to be connected to 1. Again, we are not going to create one again. We are going to pull it out from your visited node or your hash map and then establish a connection between 4 and 1. This is how you're going to be creating a deep copy of a graph. You're not going to clone it unnecessarily. You are going to maintain a hash map, and from that you will keep pulling out your nodes as and when required. How to pull out the nodes? You are going to pop the elements because we are utilizing a queue. We are going to be popping the elements whenever required. I hope the intuition is clear to you. Let us start with the code now. Ashish, do let me know if you have any doubts. I hope the intuition is clear to you. What exactly we are going to be doing, how exactly we are going to be doing. All right. Okay. So, first of all, very simple. First, let us utilize what are the, if we require any libraries for it, right? We are going to be using queues. So I am going to be using a library. So what library? I'm utilizing my collections library from which I am going to use my DQ. So import DQ. Okay, so that my queue can be created, right? Now I need to create the nodes. I showed you 1, 2, 3, 4. I need to create a structure for that node. So I'm going to be creating a class called as node. And that in turn is going to have my definition for that node, the structure definition. I'm initializing it. This is just the structure, right? Nothing else. So self, I am creating a pointer with value 0 and another pointer called as neighbors. Neighbors. Okay, neighbors. And I am giving this as none. All right. So this is done. After this, we are going to just give the structure self dot val. It's going to contain the value of that node and then the neighbors. The neighbors, Neighbors. The neighbors are going to be, if neighbors are present, then that neighbor is going to be reflecting. If neighbor is not present, then we are going to give it as none. So neighbors is equal to neighbors. If neighbors is none, if not, if neighbors is not none. Okay, so we are going to put up the neighbors here in case it is not none. If it is none, then what will we do? We are just going to leave a empty list there. All right, if neighbors are not none, fill it up with the neighbors list. If no neighbors are found, then just leave it empty. All right, that's what it says. Now let us create a function for cloning your graph. So define clone graph. Now here we are going to be keeping a track of your visited nodes, right? So we will be passing the node as the parameter. After that, first thing we are going to say, if there are no nodes in your graph, what do we do? If not node, then return none. That means we will just inform no nodes there. So we are going to return none. Now, apart from that, I told you we need to maintain a hash map or a dictionary for all the visited nodes. So what am I going to do? I'm going to create a dictionary visited and I am going to leave it empty as of now. As and when we encounter nodes, we are going to keep putting it in visited. All right. Now let us create the first node and add it to our dictionary visited. So we'll create the first node. Clone is equal to node. This is our structure, right? So I'm calling that structure node. According to that node, whatever value we have inside that node, that's going to be put up here. Node.val. Okay, now the clone has been created. We need to push it into our dictionary now. So visited node. Okay, visited node is equal to, what are we pushing here? Clone. So into this dictionary, we are pushing our very first node, which we just cloned now. Okay, this is done. Dictionary created. Next comes the creation of our queue, right? So how to create our queue? We have already imported DQ there, QUEUE. So I'm utilizing DQ library to create my queue, which is going to have my node inside it. The node which we just cloned, we are going to put that there. All right. Now, while there is something in my queue, while queue is present, what we are going to do, we are starting a variable called current, and that current is going to pop the element which we just cloned. Okay, so let us pop it, queue dot pop left. Okay, so we are popping out that element. Now, based on whatever element we popped, we are going to look for all of its neighbors and start making connections. Okay, so for the element which we popped, if for the element which we popped, let's have the let's process the neighbors. So for neighbor, NEI, for neighbor in your current is whatever we popped, right? Current dot neighbors. So that current node can have more than one neighbors. So for one neighbor among the other neighbors, if neighbor is present, it's not present in your visited, not in visited, then what we'll do? We are going to clone it, right? If it is not present in your dictionary, then we will clone it. So we will create your neighbor copy, NEIGHBOR, neighbor copy. And what will we do? We are going to create it in the form of a node, right? We are going to call the structure node. And in that, we are going to say neighbor val, NEIGHBOR. Whatever value is inside it, it's just utilizing that value, creating a copy. And that we are going to push into your visited. After creating, what will we do? We are going to push it in neighbor. But this is happening only if it's not available in your visited, then we are cloning it. After cloning it, we are going to push a copy of it in your dictionary or your hash map. Neighbor copy. Okay, the copy has been pushed now. After that, we are also going to append it or update your queue. So we are going to update your queue with the neighbor, append neighbor. Whatever neighbor we just cloned, we are also going to add that value to our queue. So our queue is not going to be empty. It's going to always keep having an element and its neighbor. Then neighbor element, we are going to keep popping it, finding its neighbors, checking our dictionary. If neighbor is present, pull it here. If neighbor is not present, create a clone and then add it to the dictionary. So this is a cycle that is going on. So now we appended your neighbor. After your neighbor is appended, now we need to add the neighbor's copy to our current node's neighbors list, right? In case our current neighbor is also a neighbor to someone else. So we need to establish that connection, right? So what we do is we are going to use visited CURR for the current visited dot neighbors, whatever neighbors we have, we are going to append that as a visited neighbor. Okay, as a visited neighbor. That means our current neighbor can also be a neighbor to someone else. That I already showed you, right? 1, 2, 3, 4. I showed you the interconnection. So if such kind of interconnection exists, then our current neighbor can be a neighbor to another node also. So that's what we are just adding to the list. So once this is done, we are going to return your clone. Return your clone. Whatever we clone, we are just returning it. All right, this is our function. Our function is now complete. Now let us create an original graph, okay? Assume that this is the input that's given to you all, for which you have to create the clone. So to create the original graph, I showed you the 1, 2, 3, 4. We'll just create the same graph. So we had 4 nodes, right? So node 1 is equal to node 1. That's the value it's going to carry. Then let me just copy this and paste it 4 times. Okay, so node 1, 2 will hold 2 value. Then node 3 will have node 3 as the value. And node 4 is going to have node 4 as the value. Okay, this is just the creation part. Assume it's the input given to you all. Okay, then we are going to set up the neighbors. So to set up the neighbors, node 1 dot neighbor. Who is the neighbor of node 1? Okay, we are going to mention that node 1 neighbors. So just look at this drawing and you'll understand that who are going to be the neighbors. 1, 2, 3, 4, and 1. So here, what are we doing? We are correlating the neighbors for your node 1. So when we are looking at your node 1, who are the neighbors of your node 1? For node 1, we have 2 and 4 as your neighbor, right? So we are going to mention that. Node 2, comma, node 4. They both are your neighbors for node 1. Then let us do that for your node 2. Then do it for node 3 and do it for node 4. Okay, for node 1 we are done, node 2. Now look at node 2. We have 1 and 3 as the neighbor. So node 1 and node 3 as the neighbor. All right. So for node 3, who are the neighbors? For node 3, we have 2 and 4 as the neighbor, right? So we have 2 and 4 as the neighbor for node 3. For node 4, who's the neighbor? For node 4, we have 1 and 3 as the neighbor. So let us give 1 and 3 as the neighbor. Okay, this was our input. Now we need to clone this. We need to clone this 1, 2, 4, 3. 1, 2, 3, 4, we need to clone it. So what we are going to do, let us create a print statement also. I'll create a function in which I'll give define print graph. Okay. And we are going to print all of the nodes and also visited. I'm going to pass my dictionary and in that let me give none because we are going to pass an empty dictionary in the beginning, right? So if visited is none. Okay, in case there is nothing in our visited dictionary, then visited is equal to, we are going to convert it to a set. We are not going to keep it as a dictionary. We are going to convert it to a set. Then the data type set, right? So if a data structure set, right? So if node is in visited, okay, if node is present in visited, then we are going to return whatever value is present in that visited node. All right. So once that is visited, then visited dot add, we are going to add the value, whatever node value we have, right? We are going to add it. Visited dot add is node. So once that is added, let's just print it. So print f. So I'll give it as node and then I will print whatever node value is there inside it, right? And then I will give this arrow mark and then print its neighbors also. I'm going to print its neighbors also. So how to print the neighbors? Just give it as NEIGHBORS. Okay, it'll print the neighbors also for me. Once the neighbors are printed, I am going to look at the values that I can get. N dot val, that is my node value for n in node dot neighbors, right? So we have our neighbors listed in the dictionary. From there, it will pick out the values for me. Then for every neighbor, we are going to, in your node of neighbors, we are going to print it for every neighbor so that all the neighbors are printed. Okay, so print graph. Just calling the function print graph and it's going to print your neighbor from the visited hash map or your dictionary. It's going to print the neighbor from the visited hash map or dictionary. So let me print the original graph also so that you can compare it that there's no change. Original graph, print graph. And what have we stored it as? We have stored it as node 1, right? So let me print this node 1. And then I am going to print the cloned graph also. Cloned, I'm calling my function cloned, right? So what is the function name we have given? we have given it as clone graph. So I'm calling it cloned is equal to clone graph. In the bracket, we need to pass the node, right? So I'm passing node 1. Next, let us ask it to print. So print, let me give this as clone graph. Okay, you can compare both of them that if they are exactly the same. And then let me print graph clone. Okay, I'm going to print the graph clone. Let's go ahead. What mistake did I do here? Node, node dot val, then I'm passing it to the neighbors and n dot val for n in node dot neighbors. Let us just check the spellings. We have the node, then we are having node dot val. Okay, let's just check the spellings from the beginning. From collections imported DQ, then we are taking your node structure definition, initializing it. We are initializing your neighbors also. Then self.val equals val. Then neighbors we are initializing. Neighbors, if neighbor in neighbors, if it's not none, then if it's none, then we are going to keep it empty, or else we are going to have your neighbors there. Okay. Then we are cloning your graph. If not node, then we will return none. Then we have created your visited dictionary. Then we created the first node's clone, node.val. And after that, we are pushing that into your visited also. Then we created your queue. Q is equal to dq, and in that we pushed your node. Then while you have a queue, current is equal to, we are popping the left of the queue. And then for neighbor in your current dot neighbors, we are looking at if scenario, if neighbor is not visited, not in visited, then we are going to create a copy of the neighbor utilizing node neighbor 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 dot val. Okay, then we have pushed it into visited. Neighbor is equal to neighbor copy and q dot append neighbor. All right, then we are moving your current visited current dot neighbors dot appending it to your visited neighbor. Then we are returning the clone. Okay. The if cases. All right. Let's look at any other typos as well in case. Just checking the indentation also. All right. Now, we need to have the list I will just rerun the runtime. I am just reinitializing the kernel. Initializing the runtime. All right. Okay. So now here you can see the original graph and exactly we cloned the graph as it is. Okay. So 2, 4, 1, 3, 2, 4, and 1, 3. Exactly the same neighbors, same connections. Right. So what this avoided is whenever there is an existing clone, we avoided creating another redundant copy of it. We connected it by checking it in the dictionary. That's the reason we utilized your breadth first search. Q was utilized because of it. And then we utilize the Q functions, that is popping, to get rid of the elements and look for its neighbors. All right, moving to the next question that we have here, the flood fill. Okay, now imagine you all might have used paint, right? Some of the other time. Whenever you were painting, you had that little tiny bucket. You would click on that tiny bucket, choose a color, and then click on some part to fill a color, right? So how did this happen? So here, imagine that we have a grid of a few numbers. Now, these numbers represent the color of an image, of a 2D image. Okay. So in that image, we might be having random colors. Now we have to change one color to another color. For example, we have yellow and we have to change all yellows to red. But these yellows need to be interconnected to each other. We need to just change one patch, right? So one patch, we need to change that yellow to red. Now, the rule number one is that patch needs to be, all the pixels or the dots in that patch need to be interconnected. It cannot be somewhere on top, then a little on the right, little down, not like that. It needs to be in one region and it needs to be interconnected. That's rule number one to change the color. The second is it should be the given color only. That means in case we are changing yellow to red, then only if yellow is present, we need to change that to red. We cannot change black, green, maroon to red. Okay, whatever color is given to us, only that color we will be changing it to the required color. Okay, that's rule number two. Then rule number one is it needs to be interconnected. Rule number two is the points need to be interconnected. The rule number two is only the given color can be changed. Now, keeping this in mind, we have to create a program or write a program utilizing your traversal techniques of the graph. Okay. Now, which is the traversal technique we are going to be utilizing? We are going to be utilizing your DFS. Why we are utilizing your DFS is because it is a path finding, right? We need to find the path in which you have all same values of that particular color, and you are just going to change those values to the current color which is required. That is yellow values, we will change it to red values. That's what we are going to be doing. So because the use case is something like finding a path, so we are going to be utilizing your DFS here. All right. So now let us go ahead and write the function for it. Like I told you, we are going to be defining one function, that is flood fill or fill flood, whatever you want, right? For that tool to work. And then in that, we are going to treat it as it is. You can see it's a 2D grid. So when you're talking about a 2D grid, you're going to have rows and columns. It's going to be a matrix kind of thing. So rows and columns, we are going to keep your rows and columns in mind and go ahead and change the colors. We are going to only change the color for the points that are interconnected to each other. Second condition is it needs to match the color which is given. That is only change yellow. So some number would have been given. We are only going to change that number to the other color which is required. All right. Keeping in mind these 2 points, let us go ahead and create it. So first we are going to be defining the function. Okay. Let us define the function. Define flood fill. Now, what does this take? It is going to take the image or our 2D grid. And in that 2D grid, you need your source, you need your row, you need your column, you need which color needs to be changed, right? So let us give your image. Then along with that, I'm going to give the SR, that is my row, then SC, that is my column, and then I am going to give color. Okay, the color which we need to change. I'm passing 4 parameters here. After that, rows and columns. We need to know about your rows and columns. How many rows and columns we have in that grid, right? In that 2D image grid. For that, I am going to check the length of my row and length of my column, right? So rows and columns is equal to length. Image is nothing but my 2D grid. So I'm going to take the length of my image. And after that, this is going to give me the number of rows. Rows are horizontal, columns are vertical. So horizontal, I'm just going to take the length of my image. For my columns, the vertical ones, what am I going to do? I am going to take the length of my image, index value 0. Okay, I'm going to start index value 0, and then it's going to check the, for index value 0, it will check the length and give me what is my column length. So row length we have found out, column length we have found out. After finding this out, why is this necessary? Finding out the length, we need to move around your grid, right? So that our grid, we don't try and move out of our boundary of the grids. That's the reason we are having your length here. Okay, so that we don't move beyond that length. We are playing around in your grid only. Okay. Next, we are going to look at what original color do we already have in that image, which we are trying to change. So I'm going to declare original color, original color. Okay, COLOR. All right, and here this I am going to give it from the image as whatever value, the same value needs to be there in my row and in my column. That is going to be my original color. Whatever SR and whatever SC is given, that will be the original color. Now, if original color is equal to my color, whichever I'm trying to change to. If it's already belonging to that color, that is, if I'm trying to change red to yellow, that's possible. But if I try to change red to red, that's not possible. So that means if the original color is already of the color which I want to change to, then we are not going to make any change. We are just going to return the image. Simple, right? So no change, just return the image. The next thing that we are going to do is let us define your depth first search, right? So definition of your depth first search. How does depth first search work? Recursion, or it stores in a stack. So here we are going to be using your recursion on your rows and columns. Continuously, it is going to read values in your row and your column so that to check if it is of the original color, if it needs to be swapped or doesn't have to be swapped. Two things it will check. One, the points need to be interconnected, only then the change will happen. Okay. So depth first search. Now we need to know whether to move left, whether to move right, whether to move up, or whether to move down. For that, we are going to use your coordinate system for your grid. That is 0, 0 is at the starting point, right? But that's not going to help you. You need the row and column to be in such a value that whether you need to move left, right, up, or down. So whenever you have 0, 1, when your row value is 0 and your column value is 1, you're going to be moving. So let me show that how. So imagine you are having this grid here. So you have a grid 1, 1, 1. Next, you have a grid, same grid 1, 1, 0. Then you have a grid 1, 0, 1. All right. This is your grid. Now, in this grid, you have to know whether to move left, right, up, or down. So I am going to say when my row value is 0. This is my row. Okay. 0, 1, 2. This is my row. Horizontal is my row. Vertical 0, 1, 2. This is my column. Okay. This is my column. Fine. And this is my matrix. Now, if I say 0, 1, that is this element 0, 1, right? So 0 of my row and 1 of my column. That means I am moving right. You can see that we are moving right. Okay. Now, if I say 0 but minus 1, 0 and minus 1. Minus 1 is we are moving left. Positive 1, move right. Column value negative, moving left. Against. Okay. So we are moving left. Now, if I say row is 1, when I'm saying row is 1 and column is 0, what is it? We are going up. Okay. Row is 1, column is 0. We are going up. Now, when I say minus 1 and 0, we are coming. When I say 1 and 0, we are coming down. So when I say minus 1 for your row value, we need to go against. So it is up. When I'm saying 1 comma 0 for your column value, 1 is my row value, I am moving down. Moving down is positive, moving up is negative. Moving right is positive, moving left is negative for your column. Okay. So this is how we are going to describe this coordinates to mention whether we need to move in the left direction, right direction, or where exactly, up or down. Okay. So let us mention if my R is less than 0. First of all, my R needs to be less than 0. I am setting the boundaries here. First, we'll set the boundaries so that my grid search does not go out of my grid, right? If my R value is less than 0 or my R value is greater than or equal to my rows, what do we have in rows? We have the length of our row. If my R value sometimes increases more than my length, that means it is going out of the boundary of the grid, right? Or the other condition is my R value is greater than equal to rows. Okay, greater than equal to rows. First of all, R is less than 0 or C is less than 0. First, both the conditions, let's cover it. C is less than 0. This is one condition. If it is negative numbers, or R is greater than equal to rows, the length of my rows, or C is greater than equal to length of my columns, or my image R C is not equal to your original color. Whatever original color you were looking at, if it is not equal to the original color, then it is a problem. We are going to return it. Original color. Okay. If it's not equivalent to your original color, then we will return. Nothing to do, just return, plain return. Else, we are going to give image RC. We will initialize image RC as the color equivalent to your color. Whatever color you want to change, right? We are going to specify that. Now let us mention the directions. So for if you have the direction for right, of the direction for your row and the direction for your column. DRDC is your direction row, direction column. In for DRDC in, now I'm going to specify the directions. To move right, row is going to be 0 and moving right is going to be column, right? Now to move left, what am I going to do? 0 is going to be my row and minus 1 is going to be my column. I'm moving left. Right is +1, minus 1 is going to be moving left, negative, right? Then now to move down. To move down 1, 0. Row value is 1, column value is 0. 1 comma 0 is moving down. To move up, negative value of row comma 0. So if it is in any of these values, then for, let's put this in a list, then what we are going to do, we are going to move it left, right, up or down, right? So DFS R plus DR. R plus DR will be the direction for row and C plus DC will be the direction for C. Simple enough. So this is for your direction, where to move in your grid. For that, we wrote this for loop. Now after that, let us return back your DFS. So DFS, I'm going to return SR comma SC. And then we will just return the image. Return image. All right. So this is done. We have returned the image now. Now, after this is written, let us now give the example here. I'll use the same grid which I had created. So I will give image is equal to, and I need to give a 2D grid here. So image is equal to, inside this, let me create a separate list, 1 comma 1 comma 1, then 1 comma 1 comma 0, then 1 comma 0 comma 1. All right. So this is the grid that I am creating, my 2D grid. Okay. My 2D grid is created. After this, now SR, my starting point of the row SR is 1. Then my starting point for my column is also 1. All right. After that, now the color which I want to change to is 2. I want to change to 2. So let's print it now. Print original image. So once we print the original image, it's going to print the grid for me. All right, it's giving me the heading. Let's print for every row in the image. Print the row. Print a row. All right, so let me run this. For every row in the image, it's printing the row. You can see that. Now I am going to call my function flood fill. So I'll store it in result is equal to, I'm calling the function flood fill. And inside that, I am going to call my image, passing the image, the starting point of my row, the starting point of my column, and the color which it needs to change to. All right, then I am going to print the image after flood fill. For every row in result, print the row. So let us print it. So here what happened? All the columns that have been connected with value 1, it's changing to 2. But this one is not changing. Why? It's not changing because it's not interconnected with your rest of the color points. That is not connected with the rest of the color points 1. Okay. So when we are dealing with depth first search, what happened? The starting point is 1, right? A row is 1, column is 1. So when row is 1, column is 1, then what? This is 0 row, this is 0 column. So this 2 is not my starting point. This is my starting point, 1 and 1. That means this 2 is my starting point. So depth first search, it cannot go any deeper. So it moves up. This 2 is then colored and then it moves left. It moves right. Then this 2 is colored. Now this has already been visited. Then this is also visited. Then it moves left. Then it moves left. Then this is colored. Then after this is changed, it goes deeper. This is colored. Then again it goes deeper. Then this is colored. and it stops. Nothing else to do. So it stops, right? It is not going to come here. Only because these are connected, depth first search works here. All right. I hope that you have understood this. Any doubts, Ashish? Do let me know if you have any doubts. All right, let's move to the next question now. The next question here is we need to find the number of connected components in a 2D grid. Connected components, assume that you are having water everywhere and there are certain islands. We need to find which islands are connected now. Okay, so here the concept is very much similar to our previous problem, like how we changed only the color of the connected points. Here we are just going to count the collected points. That's going to be the difference. Here we change the color. Here we are going to take the count of the collected points and we are going to address them as your islands. All right. So what is the function here? Same thing. We are going to be doing your DFS here. Depth first search. We are going to go deeper and deeper into your grid and search for the connected points. So let us start with your function definition. We have def number of islands. We are counting the number of islands. We are passing your grid here. Nothing else, 2D grid to be passed. After that, you are going to get to know your boundaries, your rows and columns, right? So for that, rows, comma, columns, I am going to take the length of it. So length of my grid is going to give the rows and length of my grid's index is going to give my columns. Grid index 0. So that is going to give the length of my column 0. Okay. So rows and columns, I've got it. Then I need to keep the count of the number of islands. So count is equal to 0. I'm initializing it. Now let us start off our function for our DFS, right? Defining the function DFS. What all I will pass? I will pass my row and I will pass my column. Only that. I don't have an image to be passed here, so I'm just passing the row and column. Now we need to set the boundary here, right? Setting the boundary, I should make sure that it does not go outside my grid. So if my R is less than 0, if the R value is negative, or my C value is less than 0, or my R value is greater than equal to the length of my rows, or my C value is greater than or equal to the length of my columns. So all these are the problematic solutions, right? Or my grid R and C are not equal to 1, not equal to 1. This 1 is nothing but the representation of my islands. So in case there are no islands at all, then I am going to simply return. Okay, simply return the grid as it is, nothing, no change. Now after this, I have to initialize my grid's row and column. So I am initializing the starting point, R, C, both of it, I'm initializing it to 0. Okay, initializing RC to 0. Now after that, let us set the direction for DR and DC. The direction for row and column in, let us describe the directions. What was the description? If my row is 0, column is 1, I'm moving right. How to move left now? My row needs to be 0, my column needs to be minus. My row needs to be 0 and my column needs to be minus 1. Then I can move left, opposite direction. Then if I want to move down, what happens? My row is 1 and my column will be 0. If I want to move up, then my row is going to be a negative 1 and my column is going to be 0. Okay, so this is going to give me the direction for row and direction for column. So once that is done, let us utilize your DFS and add the values to your existing row. I will add DR so that the direction is taken. To your existing column, I will add DC so that the direction is taken. Simple enough. DFS. So we are running your DFS there. Okay. Now for every row, I have to check for your values, right? I need to check how many ones we have. We need to count it. So for R in a range, so how many ever rows we have, so many rows your for loop is going to run. Inside that, another for loop we are running for your columns. For C in range, how many ever columns we have, the length of your columns. For that, it's going to run. If my grid RC is equal to 1, that is, it has the number 1 in it, that means the islands, what am I going to do? I need to count them, right? And they need to be interconnected also. So I am going to count and increase it as plus equal to 1. I'm going to increase the count by 1. Every time I encounter a number 1, I'm going to increase the count saying I found a island there. Then I am going to run my function DFS as a recursive function. That's why I'm calling DFS again and passing my rows and columns again. Okay, DFS, row column. Finally, what are we going to do? We are going to return your count. Return the count. This is going to give us the count of your uh, islands. Okay, it's going to give the count of your islands. So for loop, we have created this. And now let us create your grid. So your grid is going to be, okay. So inside the grid, let us put 1, then 1, 0. So ones are your islands, right? Then 0, it needs to count those ones. And then 0. All right. So 1, 2, 3. Fine. Next, I'm going to count 1, 1, comma, 1, 1. Then I have 3 zeros. All right. Then I am going to put your 2 zeros, 2 zeros and 1, number 1 here. And again, let me add 2 zeros. All right, another grid is done. Another row here. Let's have 0, then 0, then 0, then 1, and finally 1. All right, so now this grid is complete. Let us print the original grid. So print original grid. So it's going to for the loop remains the same. For row in grid, print the row. Then I am assigning your result. I am calling the function num islands, passing the grid in it. And then I am going to print the grid here, right? So this is not going to work this way. Print, I need to print every for loop. Num islands grid. So I have to give for a row in grid, for row in grid, print per row. Okay. So result is going to be num islands grid, then print slash n number of islands, LANDS, islands, and we are going to have your result here. Result. It's going to get printed here, and we are printing for row in grid. Okay, let's run it. So here you can see why is it giving none there? For row in grids. Number of num islands. ISLANDS. For row in grid, print row. What went wrong here? Let's just check it here. So rows, columns, we are taking the length of the grid. We are taking 0 for DFS. R and C we are passing. If R is less than 0 or C is less than 0 or C is greater than equal to your columns, or your R is greater than equal to your rows, or the grid is RC not equivalent to 1, we are returning it. All right, fair enough. Then grid RC is equal to 0. For DRDC in, and we are having 0, 0, 1, then 0, -1, then 1, 0, and -1, 0. DFS is going to be R plus DR and C plus DC. Okay. For R in range rows, for C in range columns, we are going to have, if grid is RC equal to 1, then we are going to count plus equal to 1, DFS RC, returning the count. Okay. Let me just reiterate this again. Let's see what went wrong. All right, number of islands, 3. So what did it do? It counted, connected 1 to, this is counted as 1, then 2, then connection here 3. So number of islands, we have 3 islands. All the connected ones it counted. Next, we need to figure out the max area of an island. So when we are talking about max area of an island, concept again remains the same. We are going to be doing pathfinding, counting. So given a 2D grid representing a map of ones, 1 is going to be your land, zeros is going to be your water. Return the maximum area of an island in the grid. An island is a group of connected ones. It can be either connected horizontally or vertically, but you may assume all 4 edges of the grid are surrounded by water. The next thing is, first it needs to be interconnected and all the 4 edges need to be surrounded by water. Only then you can count that as an island, and then you need to count the maximum land, island with the maximum land. So maximum ones you need to count who are interconnected, maximum ones who are interconnected. So the concept remains the same. We will use your DFS. It's going to be a recursive function. So first we are going to check the grid, and to the grid we are going to check the length. We will then make sure that it does not step outside the boundary. Then we are going to decide the direction. DR and DC will be decided. Once that is done, we are going to run your for loop throughout the loops. That is through the loops of rows and through the loop of columns, for loop. Okay, so let us go ahead and quickly start with it. defining the max area of island. Defining the max area of island grid. Okay, so this is the name that we are going to be calling also. So let me just copy this and put it as result is equal to this. Okay, whenever it's necessary, we are going to be utilizing that. Fine. Max area of the grid. In this first, we will check your rows and columns. For that, we need the length. Rows and columns is equal to length of the grid will give us columns. And then length of my grid index 0 will give us the column. Okay. So we have the rows and columns length here. Then the max area. Earlier we took the count. Here we are taking the max area is equal to 0. It needs to be connected. Maximum number of ones we are going to be counting, the connected ones. Okay, this is done. So first part is done. Now let's declare the function DFS. DFS. Inside that R comma C, that's what I'm going to pass. And in this first we will set the boundary. So if R is less than 0 or C is less than 0 or R is greater than or equal to your rows or C is greater than or equal to your columns or the grid R C is not equal to 1. Okay, not equal to 1. Then what are we going to do? We are just going to return 0. Nothing, just return 0. After that, we need to mark or initialize your grid. So we are going to mark it as a grid, the starting point, right? RC. Here, the starting point, we are going to take it as 0 because it needs to visit all the rows, all the columns. So starting point for row and column is 0, 0. Okay. Once it's visited, area is equal to 1. I'm initializing the area as 1. Then the direction for dr, dc in. Okay. For dr, dc in, row is 0, column is 1. It's going to move right. Then a row is 0, column is -1. It is going to move left. Then a row is 1, column is 0. It is going to move down. Then row is -1, column is 0. It is going to move up. All right. Let's put this in a list. Okay, once we have put this in the list, let us assign the area. Area plus equal to, there we did count plus plus. Here we are doing area. We are counting the area. So DFS, it is going to take R plus DR, the direction for row, then C plus DC, the direction for our column. When this is done, we will return the area. Return area. All right, now let's run it throughout your loop. So to run it throughout the loop for R in a range of your rows, whatever length is, then for C in a range of your columns, whatever the length is for columns, what we are going to be doing is we are going to run your grid. If grid is R, C, and it's equal to 1, we are going to only count ones, right? That two who are interconnected. Then we are going to figure out your max area equal to, we will take the max from the max area, whatever had been computed earlier, and we will run the recursive call DFS R comma C. This is going to run unless and until our entire grid is exhausted. Once the grid is exhausted, it will stop running and it will pick out the max area for us. That's why we are using the max function here. Okay. Once we figure out the max area, it is going to return the max area to us. Okay. Now let us declare the grid. Grid is equal to, inside this, let me declare the grid. Zero, zero, zero. Okay. In this zeros, let me change this to 1. So this is done. First row done. Then second row, uh, we will change this to 1. And again, next row, let us change this to 1. So now, let us change this to 1 and also this to 1. After that, uh, here we will have only zeros. And then this is a grid that we are passing as input, right? Then the last 3, we will have it as ones. Okay, last 3 ones. Okay, and then let me put 1 here and 1 0 here. All right, this is my grid. Now here you can see which are the ones that are connected, right? So let's count this. 1, 2, 3, 4, 5, 6. Ones are connected, 6. The island is 6. Here also they are connected, 1, 2, 3, 4, 5. 5 connected, and here one solo one. So between 5, 1, and 6, which is the max? That's what it is going to pull out here. The max it's going to pull out here is from that particular 5, 6, and 1. So you know that it's going to pull out 6. So maximum island that we are going to be getting here is 6. So let's print it. Define print grid. Inside this, I am passing the grid. Print grid. Let's give 1 is land and 0 is water. Okay. After that, for a row in grid, print a row. Okay. And for row in grid, print, instead of giving a row, let me give a cell in row, right? Every cell, let's print it. So cell for cell in row. For every cell, it's going to print it. Then after that, let's put this in a list. Okay, for every row, let's print it. And then print. Now let's print the initial state. Initial state, and then let me print the grid. That is the grid. Let me print it. And then we are going to use your result max area of island grid, and then let's print it. Print F, maximum island area is the result. Let's run it. So here you can see the maximum island area is 6. Like you can see here, 1, 2, 3, 4, 5, 6, right? Let's utilize DFS to find this. All right, the last question here is your Pacific Atlantic water flow question. Again, this is a DFS question, right? So here you have a grid M into N matrix. And on the left hand side, you can see the dark blue is the Pacific Ocean. On the right hand side, you can see the light blue is the Atlantic Ocean. All right, so Pacific Ocean on the top left and on the bottom right, you have the Atlantic Ocean. Now you need to figure out which of these pointers, so it's raining heavily on this grid now. Once it starts raining heavily on the grid, you need to figure out on what box of the grid when the water falls, will it be able to flow both into Pacific Ocean and Atlantic Ocean. It needs to flow in both the directions, okay? It cannot flow only into one ocean. That rainwater from that block has to flow into Pacific as well as Atlantic, both. Okay, so we need to figure out which are those pointers wherein the water can flow both into Pacific and Atlantic. What is the condition? The condition is the water can flow from a height to a lower number. So here the island receives a lot of rain and the rainwater can flow to neighboring cells directly north, south, east, and west if the neighboring cell's height is less than or equal to the current cell's height. For example, if the current cell is 4, okay, it can flow to the neighboring cell only if its height is less than or equal to. So 3 is your neighboring cell, 3 is less than 4. Yes, the water can flow to 3. Then 2 is less than 3. Yes, the water can flow to 2. Then again 3 is the neighboring cell, 3 is greater than 2. So the water cannot flow here, right? So that way you need to figure out which are those cells where the water can flow and reach Pacific and Atlantic Ocean. But the condition is it needs to be the current value that you're having in hand needs to have a neighbor lesser than the current value that you're holding. Only then the water can flow into it. So we are going to be writing the program and figuring out the points wherein the water can flow. All right. So for that, what we are going to do is we will have the same DFS approach. We are going to have your rows and columns again here. So let's give the definition as Pacific, Atlantic, and we are going to pass the heights of your points, okay, the points heights. So the island pointers we are passing. Now it's raining heavily, the water has to flow into both oceans. Now which are the points which will allow us to let the water flow there? That's what we need to figure out. Okay, let's first declare your rows and columns. Let's find out the length, right? Rows, columns is equal to length of your heights. That's our grid here. Heights is our grid here. Then for length of your heights index 0, that's going to be the height of our column. Okay, once that is done, let us set to false. Now let us set the pointers that Pacific, the water is not flowing anywhere. Atlantic, the water is not flowing anywhere. So let us set it as false. False into, this is our starting point. That's why we are setting it to false, into all the columns for in range rows. Okay. And Atlantic is equal to false into columns for in range rows. So here you can see that all these pointers, right? This edge here, 5 and 5. Automatically the water is flowing into Atlantic and Pacific. Again, Atlantic and Pacific. But the rest you will have to figure out which are the other pointers. We have 2 pointers already, the edges. They are flowing into Atlantic and Pacific together. So let's figure out all the other values. Then I'm defining the DFS here, passing your RC, that is rows column, and the ocean. Which ocean is it getting into? Is it Atlantic or Pacific? I'm going to pass the ocean. So once the ocean is passed, now ocean RC, ocean RC equal to true. I'm setting it to true. There are rows and columns in my ocean RC. Now I have to set the direction for dr comma dc in. Now what are the pointers? 0 comma 1 is to move left, 0 comma -1 is to move right. Okay, for then 1 comma 0 is to move down, and 1 -1 comma 0 is to move up, right? Let's put this in the form of a list. All right. So for these values, what are we going to do? New row and new, we are setting the new row and new column address is equal to R plus dr, and this is going to be the new direction of our row, C plus DC. Okay, new columns directions have come, and we are storing it in NR and NC. Once that is done, now boundaries we have to set. If 0 is less than equal to NR less than rows, that is the value needs to be between our rows and the 0 value, and there's a and because it needs to flow in both the directions, right? So this is the condition. So it needs to be less than your new NC, the new direction has to be less than your columns value, should be between your columns value and your 0 value. It should not go less than the columns value and your 0 value. And the next condition is it should not be the ocean. It should not be outside the oceans NR and NC. It should not be outside the oceans NR NC boundary, and also beyond the heights. Beyond the heights NR NC. It cannot be beyond our NR NC of the heights. It cannot be greater than or equal to the heights existing R and C, the existing ones, right? It cannot be greater than that also. So these are so many conditions. Only then we are going to approve it as yes, the water is flowing. DFS, NR, NC, and the ocean from which it's flowing, whether it's Atlantic or Pacific, it needs to list that out. So once that is done, now we need to run our for loop for throughout our range, throughout our rows and columns. So we are going to run for R in a range of your rows, and then for your columns, rows. What are we going to do? We are going to call your DFS, and in that R comma C comma Pacific. This is only going to be running for Pacific. Same way we will run it R comma 0. I am freezing your column as 0 and running it for Pacific. Same way DFS, I'm going to run it for R comma columns -1. That is from the right hand side. I am running it for Atlantic. Atlantic is on our right and Pacific is on the left, right? So we are going to run it for both so that the water is flowing from both the sides. Only then we can consider those pointers, right? So this is us checking for it. Then for C in range, columns. DFS, here we are going to freeze your row as 0 and let your C, and then Pacific and rows is going to be -1 here. Rows -1. That means down. We are trying to evaluate down. And C, and this is for Atlantic. All right. So this is going to run. Once this is done, we will return the values, whatever we have received. Return R comma C, and this is for R in a range, whatever range of rows you are having, and for C in a range, for whatever range of columns you are having. Okay. If Pacific, that is, it should run both the sides, right? So if Pacific R C and Atlantic R C. So only if it's running in both the direction, then those pointers are going to be returned. Now let us print the grid, print grid. And in this, I am passing the heights and also the result. Okay. So here rows, comma, columns is equal to length of heights and the length of heights of 0. That is the column, right? So we have this, then let's print the heights grid. All right. I'm printing the heights grid for row in heights. So printing it with this print simple for loop, it's going to print all the heights for me. Then I need to create a result visualization, right? So wherever the water will flow from all the pointers towards both the oceans, I will replace it with an asterisk or a star. Okay. This is just for your visual understanding. Visual. Okay. Visual is equal to in this, let us give dot where it's not flowing in both the oceans. It's flowing either of the side for in a range where your columns are only flowing, right? For in a range of your rows. All right. So this I'm specifying wherever it's only flowing into your columns and not into your rows. That will have a visual of a dot. For R comma C in a result, visual R and C is going to be an asterisk. That is where it is flowing into both the oceans, that will, those pointers of the island will be represented with an asterisk. Okay. Then let me just put few print statements here. All right. So I'm putting few print statements. And after that, I am saying for a row in your visual, print it. For row in your visual, print, whether that's a dot or an asterisk, just print it. So print dot, I'm going to join it with the row. Each and every row it's going to print, right? So it's going to join it. All right, then let me get the grid that is going to be our example. The same one which I've taken above, I'm getting the grid here. And result is equal to Pacific, Atlantic, I'm calling it. And inside that, heights, I'm going to print the grid, calling my function print grid. Inside that, passing heights, comma, heights, heights, comma, result. Okay, so let's just make sure that we are having the same grid. 1 2 2 3 5 3 2 3 4 4 2 4 5 3 1 6 7 1 4 3 4 5 and 5 1 1 2 4. All right, let's run it. So here you can see that 1 2 3 4 5 6 7 pointers are having the flow, right, of your ocean into both the oceans. So let me check that. Here you can see 1 2 3 4 5 6 7, the same pointers, right? The ones shaded in yellow can flow into both the oceans. So I hope you have understood today's session. Here we are going to be stopping both DFS and BFS. I want you to go through this very clearly, and any doubts, do let me know in the next session. I don't mind going over the same problem again, right? I'll be posting this on your LMS. It'll get posted soon. And thank you for attending the session today. Good night.